Hi everyone, I welcome you again in the course of Thermodynamics. Today we are going to continue the previous lecture. In the last lecture, we were basically discussing about the vapor power cycle. So in the start of the lecture, we basically discussed about the possibility to use the Carnot cycle as the vapor power cycle. And then we discussed about the ideal Rankine cycle. And then we solved one numerical problem as well. Now moving to the next subtitle, here we are going to discuss about the deviation of the actual vapor power cycle from the idealized one. If you remember, in the last class, we discussed about the ideal Rankine cycle. And in the ideal Rankine cycle, we had four processes. The process number 1 to 2 was the isentropic compression or the isentropic work pump input. Then 2 to 3 was the constant pressure heat addition inside the boiler. 3 to 4 was the isentropic expansion in the turbine where we were getting some work output, and then 4 to 1 was the constant pressure heat rejection in the condenser. But the actual power cycle differs from the ideal Rankine cycle, as you can see in the figure here. So here if you see, we have two different cycles. We have this one which is represented by the solid line. This is the ideal one, and I have plotted another with the dotted line. So this is the actual one. So basically the actual cycle differs from the ideal one due to the irreversibilities in various components. You can see here we have the irreversibilities in the pump, in the boiler, as well as in turbine and in the condenser. So we have different issues involved in these components. That's why we are not getting the ideal Rankine cycle. Basically, when we are talking about the irreversibilities, so the two common sources of the irreversibilities are the fluid friction and the heat loss to the surrounding. When we are talking about the fluid friction causes pressure drops in the boiler. You can see here we have the pressure drop in the boiler. So the boiler is not working at the constant pressure line. Even the fluid friction will cause the pressure drop in the condenser. So you can see here we don't have any constant pressure line, rather than we have the pressure variation in the condenser. And also the fluid friction will cause the pressure drops in the piping between various components. We have different components, and these components are basically joined with different pipes, because the end of the boiler is not connected directly with the turbine. Rather than we have the piping system to join the boiler with the turbine, as well as the turbine is combined with the condenser with the piping system. So we have different piping system here. So the fluid friction will like decrease or will create the pressure drops in the boiler and the condenser and in different piping sections. As a result of these pressure drops, the steam leaves the boilers at somewhat lower pressure. So you can see here we have the pressure drop. We were assuming that we will get the steam somewhere here at higher pressure, but we are getting the steam from the boiler at the lower pressure. Also, the pressure at the turbine inlet is somewhat lower than that at the boiler exit due to the pressure drop in the connecting pipes. So you can see here the pressure drop in the condenser, this part, is usually very small. This one, to compensate for these pressure drops, this one, and this one, even in the piping system, the water must be pumped to a sufficiently higher pressure than the ideal cycle calls for. So instead of shifting somewhere here, we have to pump up to somewhere here to compensate this pressure drop, so that when we will get the pressure drop, so this line will be somewhere here, and then you'll get close to this pressure line, which is the ideal line. Sorry. So when we have to pump the water at sufficiently high pressure, so this requires a larger pump and larger work input to the pump. So basically you have to increase the work input. So we have the first source, which is the fluid friction, which will create the pressure drops. Secondly, we have the major source of the irreversibilities, and this source is basically the heat transfer or heat loss. Heat loss from the steam to the surrounding. As the steam flows through various components, so you can see here, in this region we will have the steam, like in the boiler we have the steam, then we have the turbine, and we are again dealing with the steam. And here you have the water liquid vapor mixture. So as the steam flows through various component, there is the heat loss. To maintain the same level of net work output from the turbine here, more heat needs to be transferred the steam in the boiler to compensate for these undesired heat losses. As a result, the cycle efficiency decreases. So, of particular importance, the irreversibilities occurring with the pump and turbine. Normally, when there are losses, then a pump requires a greater work input, and the turbine produces a smaller work output as a result of irreversibilities. In the case of pump, we have to provide more work, and in the case of turbine, we will get less work output due to the irreversibilities. So you can see here, this is the ideal one. This is 1 to 2s. We are assuming that the inlet condition for the pump is same for both cases, because the irreversibilities occur within the pump. So 1 to 2s, this is the ideal one, where we have the asymptotic work input, and this one is the 1 to 2a, the a for actual one. So here we have the more work input. Again here, this is the turbine led, which is 3, and this is 4s asymptotic process, and then we have the 4a, which is the actual work. So you can see here we will get the less work output compared with this one. So we have the less work output in the turbine, and we have the greater work input in the case of pump. So under ideal condition, the flow through these devices is anisotropic. The deviation of the actual pumps and the turbines from the asymptotic ones can be accounted for by utilizing asymptotic efficiencies, as we have already discussed in chapter 7 when we were discussing about the entropy. So we have two different asymptotic efficiencies here. We have the asymptotic efficiency of the pump, and then we have the asymptotic efficiency of the turbine. When we're talking about the asymptotic efficiency of the pump, so it's basically the work ideal divided by the actual work, or we can say it's simply H2S minus H1, which is the ideal work or isentropic work, divided by the actual work. So we have the enthalpy value at 2A, so it's H2A minus H1. So this is the pump work. So here you can see we have the ideal divided by the actual work. So if I have to find the actual work, so it will be the ideal work divided by the efficiency, if the efficiency is given. But for the turbine, we have the formula in a different way. We have the actual work upon the ideal work. So simply H3 minus 4A, H4A, this one, divided by H3 minus H4S. So we have like this one. So if I have to find the actual work, then I have to multiply the ideal work with the efficiency, the asymptotic efficiency. So there is a difference between the asymptotic efficiency of the pump and the asymptotic efficiency of the turbine. So please be careful. Now, here we are going to solve a question, because this question will give you the idea that how we can find the actual work if the asymptotic efficiencies are given. Okay, one more thing before we going to start this problem. There are some other factors also need to be considered in the analysis of the actual vapor cycle. In the actual condenser, we have the condenser, the actual one, where we are basically transferring the heat uh, from the mixture to the surrounding one. The liquid is usually subcooled to prevent the onset the cavitation. We have the process of cavitation, and we have to avoid the cavitation process. Normally, the cavitation occurs when the localized pressure is less than the saturation pressure. Then there will be formation of bubbles. Also, there are some rapid vaporization and condensation of the fluid at the low pressure side of the pump impeller. This all basically creates the issues, and they can damage the pump. There are some additional losses that can be occur at the bearing between the moving parts as a result of friction, steam that leaks out during the cycle, and the air that leaks into the condenser, like represent two other sources of the losses. So we have different type of losses, uh, which can be analyzed when we are dealing with the actual cycle. So here in the example, if you see, we have a steam power plant operates on a cycle shown in the figure. I can show you. I will show you the figure in the next slide. If the asymptotic efficiency of the turbine is given, so we have the asymptotic efficiency of the turbine, which is the 87%. So it's mean the turbine is not working 100%. So you will not get the asymptotic process in the turbine. Then we will get 0.87 asymptotic efficiency of the turbine. Same way, we have the asymptotic efficiency of the pump, which is the 85% or 0.85. Now you have to determine the thermal efficiency of the cycle. So whenever the asymptotic efficiency is given, then we have to find the actual work rather than the ideal work. We will find the ideal work in the question, but we have to find the actual work to find out the actual thermal efficiency of the cycle. And then we have to find the net power output of the on the plant for the mass flow rate of 15 kilogram per second. So first we have to find the efficiency, and then we have to find the net power output in terms of kilojoule or kilowatt, because the mass flow rate is already given. So here, if you see the diagram, so this is the diagram based on the data given here. Sorry, this one. So the data is given, like we have the pump, we have the 9 kilopascal and 38 degree centigrade. So this is the state of 1. So basically this is not the saturated liquid. Then we have the pump with efficiency of 85%. At point number 2 or state number 2, we have the 16 megapascal. At state 3, so state 2 and state 3 both are different one. And ideal one, we have only one state. So you can see here we have the 16 megapascal, and then we have the 15.9 megapascal with 35 degree Celsius temperature. Then at point number 4, the outlet of the boiler, we have 15.2. So you can see the pressure is dropped from 15.9 to 15.2, and the temperature is increased to 625 degree Celsius. This is point number 4. And again, the point number 5 is different from the point number 4. We have the 15 megapascal, so it's mean we have the pressure drop again, and then we have 600 degrees Celsius. There's some noise outside, so please avoid this one. So we have the pressure at 4, and with the pressure at 5. So basically you can see the outlet of the pressure outlet at the boiler is not same as the inlet of the turbine. So we have the pressure drop here as well, and even the temperature drop as well. Then we have the turbine with the efficiency of 87%, and then we have this point state number 6, which is 10 kilopascal, and then we have the condenser, but at the end of the condenser we have the 9 kilopascal. So you can see the pressure is drop inside the condenser as well, 10 to 9. So when I'm going to draw the test diagram, so it will be like this one. So you can see here, the point number 1 is somewhere here. It's not at somewhere here at the constant pressure line. If you can see the complete diagram, so you can see the deviation from the ideal cycle. So we have the point number 1, which is the 9 kilopascal and 38 degrees Celsius. Now this is the asymptotic work, but right now we are getting this work, which is the 2. 2s is basically the ideal one, the asymptotic work. So at 2 we have the state which is 16 megapascal. At point number 3, you can see this is 16 and this is 15.9 and 35 degrees Celsius. So it means the pressure is again drop. So point number 3 is somewhere at the lower pressure, and at the bottom side. This is the inlet of the boiler, and then we have the boiler, but actually it should be like this one, but we have the pressure top, and, and we are getting this value rather than this one. So we have the point number 4, which is 15.2 and 625. Then we have the point number 5, which is 15 megapascal and 600. So basically we have to check all these values, and then we will get the corresponding enthalpy values from the table. Then instead of 6s, this one, the isentropic process, we are getting this point, which is 6, and then again the point number 1. So there's a pressure drop again. So how we can proceed with this one? We have to check the values of the enthalpies, because if you know the enthalpies at all points, then you can easily solve this question. So first of all, we have to check the enthalpies. Let's first at state number 1. So for the state number 1, or like work, the work input to the pump, it will be simply the ideal work pump n divided by the efficiency of the pump, isentropic efficiency of the pump, as we discussed here. You can see the actual upon ideal is the efficiency, isentropic efficiency. So if you have to find the actual work, simply have to shift this one here, and then I would divide the isentropic work with the isentropic efficiency of the pump. So here I am going to check the actual pump work input, simply the ideal work divided by the efficiency of the pump. So as we know that the ideal work input is simply V1 P2 minus P1 upon the efficiency. So here I am going to check the value of the V1 from the given condition. So we have the given condition of sorry, we have the given condition of what is the given condition of 9 kilopascal and 38 degree Celsius. Now actually we have to find the value of V1 and P2 minus P1 are already given. So as we know, this is pump. So for pump, this is like this is P2, the outside of the pump, which is 16 megapascal, and we have the 9 kilopascal. So we know what is P2 and P1 for the pump, but what about the V1? So here we have the what you can say the pressure and temperature given. So first of all, we have to check the state. We have the 9 kilopascal and 38 degrees Celsius. So if I'm going to check from the stream table, so here we have the stream table. So we have the table A4 and A5. First, I'm going to check from the table A5 because the A5 is for the pressure table. So if you see here, we don't have any 9 kilopascal. We have 7.5, and then we have 10 kilopascal. But again, if you see, we have 7.5 kilopascal as a temperature. The saturation temperature is 40.29, and for 10 we have 45.81. So if we have the 9 kilopascal here, so it will be the temperature, the saturation temperature will be in between 40 and 45. Let's suppose around anything 43 or 44. But the given temperature is 38. So you can see here we have the given temperature of 38. So it's been the point number 1, or the entry of the pump is basically the compressed liquid. So it's been we have to check the value from the temperature against 38 degree Celsius. So moving back to the temperature table, which is A4. So here, if you can see, we have the 38, we have 35, and then we have the 40. So in both cases, we don't have any 38 value, so we have to basically interpolate, and then we will get the value. So when we will do the interpolation, so we will get around 0.00100, let's suppose 7, because we have 6 and we have the 8 and we have 10, so around we will get 7 here. So it's a V1. So if I'm going to check again here, so pump. So here we have the V1 0.001007 times we have 16 megapascal, and we have the 9 kilopascal. So in terms of kilo, and because we have a kilo already here, or you can multiply this one with 1000, you can multiply with this 16 by 10 power 6 divided by the efficiency, and then we will get the answer around like 18.96 or 7. So I've just rounded off, and I've written as 19 kilojoule per kilogram. So this is the pump work input. So if we have the pump work input, so because we have to find the efficiency, so we need the W net, which is the Q. W net is simply the Q in minus Q out, or simply the turbine work output minus the turbine. Pump work in. So right now we know what is the pump work input. Now we can check what is the Q in, because the efficiency formula is simply the W net upon Q in. So for the Q in, we have the H4 and H3. So here, if you know, if you can check here for this one, we have H4. So for H4 we have the data, and for H3 we have the data. So using this data and using this data, we can find the value of H4 and H3. And here we'll get the H4 and H3 equal to like 3647.6 minus 160.1 kilojoule per kilogram, and then when you will solve this one, you will get 3487.5 kilojoule per kilogram. So this is the Q in, which is the heat input to the boiler. So we have the heat input to the boiler. We have work input to the pump. We have the heat input to the boiler. Now we are going to check the work output for the pump. But before going to find the work input, so I'm just going to show you the diagram again. So here we have the 5. You can see we have the 15 megapascal and 600 degrees Celsius, and we have the 10 kilopascal. So here we will check what is the H value using this one, 15 and 600 degrees Celsius, and at the same point we will find what is the S5, the entropy at point number 5. When we know what is entropy at point number 5, and we know the process at point number 6, so we can easily check the values. So how we can proceed? Simply we will check the value of H5 at we will take the value of H5 at 15 megapascal and 600 degrees Celsius. We will check the value of enthalpy at point number 5. Then we will go to the point number 6. We will assume that the entropy at point number 6 is the same as the entropy of point number 5, as we solved in the question number 1 in the last class. Then we will check the x value if there is any x value, and then we will solve for the H6. But that H6 will be the H6S, this one, rather than this one. So we will solve for the isentropic work, and when we know what is isentropic work, then we can easily calculate the actual work, because the efficiency, isentropic efficiency of the turbine is given. So 15 megapascal and 600 degrees Celsius. So here we have the 16 megapascal, and because when we have the 16 megapascal, so it will be somewhere in the superheated region. So this is the saturated one, this is the superheated table, this one. So 15 megapascal, 3.5, then with 8, 12.5. So here we have the 15 megapascal. So you can see 15 megapascal, and we have the 600 degrees, so the H value is around 3583.1, this one. This is the H value, H5, and the S5 is 6.6796, 6.6796. This is the S value, S5. So we know what is H5, we know what is S5. So we are assuming that this S5 is equal to S6, because we are assuming that the turbine work output is the isentropic work. So S6 is basically the S5, which is equal to 6.6796. So the pressure at the turbine outlet is 10 kilopascal. You can see here we have 10 kilopascal. So moving back to the table A5. So here we have 10 kilopascal. So when we have 10 kilopascal, so you can see here the value of SF and SG. SG is 8.1488. But the given value of S6, which is equal to S5, is around 6 point something. So it's mean we have the vapor mixture region at point number 6. So first of all, we have to find the value of X6, the quality, and with the help of that quality, we will find the value of H6S. So when you will solve this complete equation, then you will get around the H6 value will be around 2115.3. So after solving all these steps, you will get 2115.3. So this is the H6S. So there is a minus sign here. So we have this one. but we have to find the actual work output. So actual work output will be the isentropic efficiency times the actual work output, because for the turbine we have the actual upon ideal, so I have to just multiply the ideal with the isentropic efficiency to get the actual work output. So simply when we have the isentropic efficiency, then we have to multiply with the H5 minus H6x. So by doing this one, you will get the actual work output. So here we have 0.87 times the H5 from the stream table, and then we have minus, and then we have H6x. I have basically didn't show some steps here. You can do it because this is the same part as we did in the question number 1. So first of all, we have to find the S5, and then S5 is equal to S6, and then we have to find the X6, and then with the help of formula which is H is equal to HF plus X HFG, we have to find the H6. So when you will do this thing, you will get the answer of 1277 kilojoule per kilogram. So right now we have the turbine output, we have the turbine input, we have the Q input. So what about the W net? W net will be the turbine output minus the turbine input. So we have what is the turbine output? We have the what is we know what is we know about the turbine input as well. So ultimately we will get around 1258 kilojoule per kilogram. So this is the work net. So if we know what is the work net, so we can easily calculate the efficiency. So efficiency will be equal to the work net, which is this one, divided by the Q in, and we have already calculated what is Q in. So here we have the efficiency, the thermal efficiency, which is W net upon Q in, and when you will put the values, you will get around 0.361 or 36.1%. So this is the efficiency of the cycle, the actual cycle. If we are going to assume this actual cycle with the ideal one, if we are assuming that there is no pressure drop and there is no heat loss or there are no irreversibilities, then if we solve this one with the ideal cycle, then we will get around 43%. We will get around 43% of the efficiency. So due to the irreversibilities, you can see the efficiency is dropped to 36. So around 7% 7% efficiency is dropped. And because we are generating the electricity from the Weber power cycle, so every drop in the efficiency matters a lot. Now right now we have calculated the efficiency, which is around like 36.1%. Now in the question there was another part to find out the W net, the work output, but the complete one. Now the mass flow rate was given, and right now the W net, which is this one, W net is 1258 kilojoule per kilogram. So if I'm going to multiply this one with the mass flow rate, then kilogram and this kilogram will be cancelled out, and then we will get kilojoule per second. And then we can easily calculate the power produced by the power plant. So it will be like this one. The power produced by this power plant is simply the mass flow rate times the W net, which is 15 kilogram per second times 1258 per kilogram, and then you will get around 18.9 megawatt. So this is the power produced by this power plant. After solving this one, we are going to solve one more question. So here, if you see, we have a steam power plant that operates on a simple ideal Rankine cycle and has a net power output of 45 megawatt. Already the work output is given, which is the power output. Steam enters the turbine at 7 megapascal and 500 degrees Celsius. So you can see steam enters the turbine. So it's basically the point number 3 at 7 megapascal and 500 degrees Celsius, and is cooled in the condenser at a pressure of 10 kilopascal. So both pressures are given, which is 7 megapascal and 10 kilopascal. Because in the ideal Rankine cycle, we need only 2 pressures. So 7 megapascal and 10 kilopascal. Now here, if you see, the condenser is cooled by running cooling water from a lake through the tubes of the condenser at a rate of 2000 kilogram per second. So this 2000 kilogram per second is not the steam flow rate, it is the water flow rate that is used to extract the heat from the condenser. Now you have to show the cycle on the test diagram with respect to the saturation line and determine the thermal efficiency, the mass flow rate of the steam and mass flow rate of the steam, and the temperature rise of the cooling water. So this is the cooling water, which is this 2000 kilogram per second. So it's very easy. Like question number 1 and question number 2, we can easily solve this one because the 7 megapascal is given and 500 degrees Celsius is given, and we have the 10 kilopascal. So assuming the ideal Rankine cycle, so we know the point number 1 is on the saturated liquid line, so we can easily find out what is the H1. We can easily find out what is V1 as well at 10 kilopascal. And then we have the point number 2. So with the help of isentropic work, it is V1 P2 minus P1. We will find what is the value at point number 2. Then with the help of given data, 7 megapascal and 500 degrees Celsius, we will find what is H3. Then we will find S3 as well at point number 3. And then assuming that the S4 is S3, and then we will proceed to find the S4 and then H4. So here if you see with the H1, which is the HF at 10 kilopascal, this one. So you will get the answer of 191.81. You will get the V1 as VF at this point, and the answer is 0.00101 meter cube per kilogram. As we know, the pump work input is always V1 P2 minus P1. So we have V1, we have P2 minus P1, we have 7 megapascal and 10 kilopascal. So we have this one, and then we will get 7.06 kilojoule per kilogram. And also we know that the pump work input is also equal to H2 minus H1 as well. We have H2 minus H1, and it's again equal to the pump input. So by rearranging the equation, we can get the value of H2, and the H2 value will be around 198.87. So we know what is H1, we know what is H2. So with the help of data, we can find the H3 as well. So at the given pressure and the temperature, which is 7 megapascal and 500 degrees Celsius, we can easily calculate what is H3, and we can find out what is S3. So this is the state number 3. Now we know what is S3. So equating this S3 equal to S4, and with the 10 kilopascal, first of all we will check the state, and then we will find out the H4. If you will check the value at 10 kilopascal, you will find that the S4 is like in between, and the S4 lies between the SG and SF. So it means you are getting the vapor liquid mixture. So you have to find the X4 first. So X4 will be S4 minus SF upon SFG, and this is the basic formula. And then you will find what is X4. When you know what is X4, then with the help of this and this formula, you will find what is H4. So you will get the H4, which is 2153.6 kilojoule per kilogram. So in all Rankine questions, Rankine vapor power cycle questions, you are basically following the same procedure. Now we know what is H1, H2, H3, H4. Then we can easily calculate what is the Q in, Q out, and even W in, W out, and W net as well. So Q in simply H3 minus H2. So we know what is H3, we know what is H2. So we'll get this answer. The Q out will be H4 minus H1. So you will get this answer. And W net is Q in minus Q out. And you know what is Q in and Q out. So you'll get the answer of 1250.7 kilojoule per kilogram. Now when you know what is W net, then you can easily calculate the thermal efficiency, which is W net upon Q in, and then you will get the 38.9% of the thermal efficiency. So this is the easiest part to find out the thermal efficiency. In the next part, here he is asking about to find the mass flow rate of the steam. Mass flow rate of the steam, and already the 45 megawatt is given. So this is the W net, which is the capital one. So W net is given, and W net is equal to m dot times the W net, which is specific one. So the mass flow rate will be the W net upon the W net. This is specific one. When you will multiply this one, you will get W net. So W net is simply W net upon the specific work net is equal to the mass flow rate, and in this way you can find the mass flow rate of the steam inside the pipe or inside the condenser. This is the steam which is flowing inside the cycle. Now you have to find the mass flow rate is already given for the cooling water, and you have to find the temperature rise. So here in the condenser, what happens? This is the condenser. So what happens? We have the tubes around this condenser, and this is basically a heat exchanger. So the heat from the condenser will be absorbed by the water that is circulating around this condenser. So it means the Q out from the condenser will be equal to the Q into the tubes of the cooling water. So the amount of heat wasted or rejected by this condenser will be the heat gained by the cooling water. So the heat out is simply H4 minus H1. As we know here, we already calculated the Q out is H4 minus H1. So this is the amount of the heat that is rejected from the condenser, and the same amount is gained by the cooling water. So it will be like this one. So we have Q out, and it will be M Q out. So right now we know this is the Q out, which is this one. This is per kilogram. So this is the total one. So total one is this one, kilojoule per kilogram, kilojoule per second. So this is the Q out from the condenser. So this is the Q out from the condenser, and this Q out is the Q gain by the water, and for Q gain simply MC delta T, because the water is only getting the heat and it is not going to evaporate. It's simply you will find the sensible uh, temperature, sensible heat inside the water. So only the temperature is going to increase. So you can see the temperature is going to increase up to 8.4 degrees Celsius. So simply MC delta T. So we know what is M for the cooling water, the C value for the cooling water. Water is simply 4.18 joule per kilogram Celsius, and this Q is simply the Q out from the condenser. So simply Q is equal to mc delta T, then we can easily find out what is the delta T for the cooling water, and it will be 8.4 degrees Celsius. So whatever the input temperature of the cooling water, you will get only 8.4 degrees Celsius increase in that temperature. So this is the end of today class. In the next class, we will discuss about the procedure to increase the efficiencies of the Rankine cycle. Means how we can increase the efficiencies with the help of different strategies, or with the help of different options or configuration that we can opt to increase the efficiency. Thank you.